Hi folks, today we're going to be looking at section 12.3 in the textbook, which is about doing calculus type things in polar coordinates. So to start us off, I've put sort of a generic polar graph up here. This is r as a function of theta, and theta is probably running well beyond 2 pi, right? It's going around multiple times. So, but you know, I'm basically one of those spirograph graphs that I talked about before. Well, what kinds of things do I mean by doing calculus on a graph like this? I think one of the more obvious things is if I've got a point that's, corresponds to some r and theta, then I'd kind of like to know what's the tangent line like to the graph at that point. Now, lines in polar coordinates are a little tough, so we actually usually just refer back to the Cartesian system. I want a slope and I've got a point, right? So I know the coordinates of that point, or they can be reinterpreted as x, y coordinates using r and theta. But what's the slope? What's the slope of this tangent line? That's one kind of thing that you could do calculus-like here. Another calculus-y thing that we do often is figure out the area between curves. In this case, I'll illustrate that with a place where the curve is, the area between two branches of the same curve. That's for different thetas, but we can adjust that. Maybe I should be a bit kinder about that. Let me erase and give you an example about area. Okay, here we go. Here's a nicer example of a pair of lines, or a pair of curves that are defined in polar coordinates. I haven't given equations for these, but the green graph is sort of a kidney-shaped thing. They often call that a nephroid. And the red thing is a circle. Right? So we're interested in being able to determine the area between these two things. I might mean all of the area between these two things, but often I have in mind angular limits. So you might go, say, from theta equals 0 to theta equals pi over 2. And in between those angular limits, the area that's trapped between the two curves is this stuff. Try to be careful with my striping. Okay, so how do we calculate that? Well, as you may guess, it's rather like what you did previously for finding area between two curves. You need to integrate, but you have to be careful because the way the things are defined and the polar coordinates require us to do a little change of coordinates kind of manipulation. Okay, so we've got slopes of tangent lines. We've got areas between curves. These are standard things that we've done in calculus. Just this term, we talked about arc length along a curve, and that's certainly something you could do in polar coordinates, or something you could be asked in polar coordinates. So for instance, I've talked about the area of this region. What if I just wanted to know how long is this bounding curve for that region in between here and here? That is an arc length. So we've got an area that we might like to figure out. What's in between the curves, arc lengths along the curves. I could probably have drawn a tangent line on this same picture, right, and a slope of a tangent line. So those are the three kinds of things we're going to look at. But really, before we get into that, and we'll start with the slopes, I want to back up a little bit and do just a slightly easier case. The easier case that I want to deal with first is when the curve is given parametrically. That is, you just have an x-coordinate function. X equals some function of parameter, and I almost always use t for my parameter. And you have a y-coordinate function, say g of t. And we've seen before that you can use those kinds of parametric formulations to do anything you could do with ordinary functions, but also much more. For instance, things that violate the vertical line test. So you might get I don't know why I wrote in green, but personally, I always just think about Etch-a-Sketch. You're using f of t to control the horizontal knob and g of t to control the vertical knob, and you can make your Etch-a-Sketch draw all kinds of things. So you might have a graph like that. Now, if you have let's start ourselves at the origin, so it looks like that. It looks like a spiral, but it's kind of getting not as fast, not as large of a slope, not expanding all that fast after you get past the first beginning part. That was said really poorly, but you get the idea. We've just got some arbitrary graph on here. How about the slope along that? That is, if we had some particular point on the graph corresponding to a particular value of the t parameter. So this guy might be coordinates f of t naught and g of t naught. How do we figure out the slope here? Well, that turns out to be pretty easy. What's the direction of motion if you imagine this thing swinging out there? Well, at this point in location, my x-coordinate apparently is getting smaller. I'm heading that way, right? And my y-coordinate is getting larger. The numbers about how your x and y coordinates are changing are just the derivatives, right? So at time t naught, this guy is, its x-coordinate is changing by a factor of f prime at t naught. And its y-coordinate is changing by a factor of g prime at t naught. We can see that most easily by thinking about the Leibniz notation. Why? Because, well, x is f of t. So dx dt, that's f prime of t. Also, y is g of t, you know? And so dy dt, that's g prime. Now what I'm asking you for the slope of a tangent line is literally dy over dx. So how do we use the ingredients we've got to get that? You guessed it, you're right, dy dt over dx dt. And the power of the Leibniz notation is that these expressions that look like fractions, you can actually manipulate as though they were fractions. You can times top and bottom by dt, and that cancels off those things. But on the other hand, dy dt is something we know. It's g prime. And dx dt, the bottom of this, is something we know. It's f prime. So yeah, you can find the slope by doing what I think a lot of people wish the quotient rule was. You take the derivative of the top, you take the derivative of the bottom, that gets you the slope. You just literally compare them. Okay, so so this slope here that I was indicating, the slope of this line is, wait, do it backwards. G is in the top, so g prime of t naught over f prime at t naught. So that's actually pretty reasonable, and it turns out the computation in polar coordinates just comes from thinking about this and moving to a different version of what the things that x and y separately are equal to. So let me erase it and we'll do that. So I've just drawn up some markings to make it look like polar coordinates. You know, we've got the regular axes, but here's some lines of constant radius. And the red is supposed to be some polar function. So this guy is given by r equals a function of theta. And that point probably corresponds to some particular theta value. Probably. No, I shouldn't say probably. It does. It corresponds to some particular theta value, say theta naught. So at this value of what is effectively just our parameter, what are the x and y coordinates on that curve? Well, we've used this conversion from polar to Cartesian a few times. X is r times the cosine of theta, and y is r times the sine of theta. But that means, since r is f of theta, you can write both of them strictly in terms of theta. X is f of theta times cosine of theta, and y is f of theta times sine of theta. So doing the calculation that we just did a second ago with parametric forms, well, this is a parametric form. It's just that we're calling the parameter theta instead of t. Right? So dy dx is going to be equal to, let's just say, d by d theta of the one that's in the top. That would be f of theta times sine theta divided by the derivative with respect to theta of the thing in the bottom, which is f of theta times cos theta. Right. So long as we can take these derivatives, we're going to be set. And that's not bad, really. They're just the products of a function that we presumably know and a trig function, which we certainly know. So you just use the product rule to get the derivatives of these two things and see what comes out. So I can do it in generically. I guess I will do it generically, but I think it'll become clearest when we do an example of this. What is that top expression? It's, well, let's just call it f prime. The derivative of the first times the second thing unchanged plus the original, the unchanged version of the first times the derivative of the second thing, which for sine is cosine. And in the bottom we have, well, again, apply the product rule. So you'll have f prime times x cosine theta unchanged plus f times the derivative of cosine, which is negative sine. I'm going to just write sine though, and we'll change this to have a minus sign there. Okay. So there you go. That's an expression that's, I don't know that it's worth memorizing. You just think about it, how the expressions are going to be written as r times sine theta, and applying the product rule, and you get this for the slope of a tangent line. So yeah, let's put it to use for something that we just saw yesterday. Now, well, this is, for me, this is today, but yesterday for you. In our class time. So I hope you'll remember we got this function for the polar version of getting a parabola. Right? So this is really y equals x squared. And I'm going to call this point, let's see, theta is pi over 4, 45-degree line outward this way, and r is sine of pi over 4 over cos squared pi over 4. But you know, that's really 1, 1. Right? So we know what the slope of the tangent line is there. It's a double of 1, it's 2. So great, that's something we can calculate. I do want to point out, just because this is an awkward way to write this. Well, maybe you don't like this other way either, but you can also think of this as sine over cosine times 1 over cosine, and that's actually a familiar expression. That's secant tangent. So secant is 1 over cosine, tangent is sine over cosine. That's the same thing as the formula we just came up with that gives us a parabola. Right, so how do we work out our slope? Well, what do we do indeed? We go x is r cos theta, and y is r sine theta. But r is secant tangent theta. So that is, x can be thought of as secant theta tangent theta, darn it, out of space, cosine theta. Let me just bump like that, okay? And I'll leave more room for y so I don't have to do that again. Y is secant tangent sine. Yay. All right. So what we're going to do is figure out what dx dt is and what dy dt is. And then we're going to compare the two and cancel out the over dt's and get a slope. Suddenly I'm hating myself for bringing up the secant tangent stuff, because I probably should have had this be x is sine theta over cos squared times one more cosine. Yeah, I think I will adapt to a different way of expressing these, because just as it's easier in figuring out the derivatives. But let me see that after I erase the board and start with a clean slate. Yeah, so a little more reflection. Leaving it written all in terms of sines and cosines really is much simpler in this case, because look what happens with the x, for instance. Cosine with the cosine squared at the bottom, this simplifies to just sine theta over cos theta. And that's tangent. And this other one simplifies, whoops, I left out a 2. This other one simplifies to sine squared over cos squared, and that's tangent squared. So finding dx d theta is just taking the derivative of tangent. Derivative of tangent. Isn't that secant squared? If you can't remember it, you can always stick sine over cosine in, take this thing in, and think about the quotient rule, but it really is secant squared. And dy dt, well, that's the derivative of tangent squared, which would be the derivative of squaring, doubling, times the function that it had, or applied to the function it had on the inside. But this is a chain rule situation, right? So you also need to take the derivative of tangent, which again is secant squared. Right? So dy over dx is secant squared times 2 times tangent theta over secant squared. Let's see, the y is the top, 2 tan theta. Why am I going to write the secant squared? You see that both of them have a secant squared in them, so those are going to cancel when we put one over the other, and we end up with twice tangent of theta. Great. I had wanted to do this at a particular point so that we could see what would happen there, and the point was when theta is equal to pi over 4. Well, what does that get us? The tangent of pi over 4 is 1 over 1, and so this does, in fact, equal 2. Right, because we did know this was coming from a parabola, and I just wanted to see it work on that. We should probably do another example of this, which is slightly less artificial, something that's really appropriate to be in polar coordinates so that we can see this thing in action in its sort of native environment. Well, this is such a natural setting. This is a curve that's called a cardioid. A particular possibility is r equals 1 minus cos theta. You can see that because of the 1, this is kind of pushing the cosine theta up in the air and flipping it upside down. But so the radius does come down to 1. Sorry, the radius does come down to 0 sometimes, but it's only when cosine's value is 1. Okay, the radius is 0 when the theta is 1, which is this point here where it's dented in. And then 2 pi later, the radius comes back to 0, right? So you can imagine this as we start facing along the x-axis and we have a radius of 0, and then we move to different angles around here. When we get to 90 degrees, it turns out our radius is 1. It's because the cosine of 90 is 0. We won't be subtracting anything. When the cosine's value gets to -1, which happens when we work our way around to pointing in the theta equals pi direction, we're actually subtracting -1, so we get 2. So this, if you thought of the Cartesian coordinates of points, this is -2, 0. The other point on there was 0, 0. This is 0, 1. And, well, aside from the I don't think I need to label the origin, but let's put this one on too. X coordinate is 0, the y coordinate is -1. That happens when theta is 3 pi over 2. I don't know if I need to really draw these little scraps of lines showing directionality, but this is a nice one-to-one function over the interval 0 to 2 pi. All right, so how about we figure out what its slope is right there when we're passing through the point 0, 1. All right, so let's run through the process again. X is going to be r times the cosine of theta. Then r is 1 minus cos theta. Y is going to be r times the sine of theta. So this part is 1 minus cos theta. I feel like this is all pretty doable. We just distribute. So we'll get cos theta minus cos squared theta. And y is sine theta minus cos theta sine theta. So we can take derivatives of these things directly, or we could apply the formula that we deduced from working generically. I don't know how to, which was better. I guess they amount to the same thing. The formula comes from thinking about just product ruling this guy, right? And I guess the advantage is you only have to take the derivative of the thing that's in parentheses here once, and you get to replay that. All right, so let's try it that way. Let f of x, or f of theta, be the 1 minus cos theta. Then f prime of theta, that's going to be, well, derivative of 1 is 0. Derivative of cosine is minus sine. With that minus, we get a positive thing, so we get sine theta. Right? And the thing we had worked out for the slope, dy dx, remember the quotient rule showed up, so we had f prime of theta times, be careful, times sine. Yeah. Darn it. I haven't left enough space for this. All right. I'm going to stop and erase and continue downward from this calculation. You've seen the graph already. You've seen this development. So, yeah, that'll be a good thing to do. I thought I would take a moment while I was erasing to also just sort of transfer to the board that formula we'd come up with for dy dx. But I hope you can see that this is coming out as a product rule in the numerator over a product rule in the denominator. Remember this we were taking the derivative of f times sine of theta. So we got derivative of first times the second plus first times the derivative of the second. When we were looking at the bottom, it was the x-coordinate, so that was f times cos theta. So the derivative of the first times the second plus the first times the derivative of the second, and because of the cosine's derivative being negative sign, we get that minus sign. Okay. So let's do this with our particular functions in mind, but here's the advantage of what we're doing. I want to get the value of this derivative, this slope calculation, at a particular theta value. And the particular value in mind was theta equals pi over 2. So at theta equals pi over 2, let's see if we can calculate all these things. The derivative is the sine of pi over 2. So f prime of theta, sine of pi over 2 is 1, isn't it? The original function had pi over 2. I should say theta naught. At pi over 2, the cosine is 0, so 1 minus the cosine, that's 1. And what about the trig functions themselves? Sine of theta naught. I keep writing theta, I should probably just be writing pi over 2. But anyway, sine of pi over 2, that's 1. And the cosine of pi over 2, or theta naught, as I seem to be fond of calling it, that's 0. So what's our dy dx? The derivative times the sine, which is 1, plus the original function, which is 1, times the cosine, which is 0, divided by the derivative, which is 1, times the cosine, which is 0, plus, minus the function is 1, times the sine, which is 1. Great, so this turned out to be 1 over minus 1, or just negative 1. Now, do you remember what the cardioid looked like? Yeah, terrible graph of it. I tried to draw it carefully before, but anyway, does that, as it crossed the y-axis up there, look like it might have a slope of minus 1? Yeah, it does. So our next topic is going to be areas. Let me just remind you how we thought about areas previously when we had two functions, f of x and g of x, say. And then we had intervals, say x is a to x is b, to think about. The area between the curves and between the fixed endpoints was got by doing an integral, and it was because you could basically think about dividing the region up into a whole bunch of vertical strips. And in fact, letting the number of strips go towards infinity, which meant the width of the strips went towards something tiny. We started off with them as delta x, and then you think about that as turning into dx. So the sum of height differential times delta x, when we did through a limiting process, that morphed into the integral from a to b, in fact. I didn't even say what the sum limits were, but you know, this is just a quick review so we remember this stuff of f of x minus g of x dx. So the basic calculation, though, was to think about these pieces of area you get by thinking about dividing the thing up into vertical strips. Now, if instead of a Cartesian function, we've got something that's got rotational, that's naturally rotational, you may think about your x values, your a and b, as actually being theta values. So this might be theta equals a and theta equals b. Those are rays out of the origin, right? You still have the difference between the two functions to deal with, so you could have f of x minus g of x. But this is not going to work out if we just try to take the integral from a to b of f of x minus g of x d theta. Oh, sorry, I should say f of theta, g of theta, d theta. This is wrong. Let me make sure I indicate that graphically. This is not what we want. Why? Because that kind of thinking with vertical strips led us to this formula. And now we do not have vertical strips anymore. What we have in here is strips who are tapered. They're small in the middle and they're getting bigger as you go out. It's most obvious if you think about an integral where the inner function is just 0. In that case, if you extend these all the way down towards the origin, you see that they're all converging at that one point. So the problem is that those pieces that the area is made up of are not rectangles, they're actually triangles. And that's what we're going to need to use. What is the area of one of these triangles? So what I'm going to do is figure out the area inside of one function, and then subtract from it the area inside the other. And that is a trick that we did before at this stage too. We just figured out the area under f of x and the area under g of x and subtracted to get this kind of formula. All right, so how big is a triangle? If it is some differential amount theta wide, but its radius is some r, a function of theta. Here's the problem. Depending on where you are along the thing, d theta represents an angular change. But the actual height of this triangle, what we want to use is base times height over 2. But the actual height of this thing depends on how far out you are along the radial direction as well as what d theta is. So what is going on is that d theta, I shouldn't say it this way, the height of this rectangle, of this triangular piece is basically r times d theta. The farther out you go, the bigger the height gets, the bigger that section along the arc is. And you can treat it, because we're playing with differentials, you can treat this as just being a right triangle with the angle theta down here. H is just r d theta. Great, so what is this is actually going back to something we said in the very beginning of class. If you want to get any kind of physical quantity, you figure out the differential version of that thing and you integrate to get it. So what I'm actually showing you is the differential area. Base times height over 2, the base is r of theta. The height is r of theta times d theta. And there's the over 2 bit. So in other words, r squared of theta, or r of theta squared over 2, 1/2 of r squared of theta d theta. So I think I'm ready to write out the actual formula for the area inside of a curve that's given in polar forms. Suppose we've got our r is equal to f of theta. Defining something, and again we're working between one value of theta, theta equals a, and another, theta equals b. This volume in here, or excuse me, I said volume, I do mean area. That area is the integral from a to b of r of theta squared d theta, and there's a factor of a half in that that I almost forgot about. Let's verify, right? Let's see, let's make this work, check this works for something we know well. Suppose r doesn't actually depend on theta, but it's just a constant. R of theta is 1. Then what we get in here is 1 squared d theta. Well, that's just d theta, right? I keep dropping that 1/2. Don't let me do that. Integral from a to b of d theta. What would that be? Well, if you integrate d theta, you'll get theta. So this is 1/2 of theta evaluated between these limits, b to a. So it's 1/2 of b minus a. Let's do a piece of this that we should know. If I draw the thing we're talking about, r equals 1 is just a circle of radius 1, right? Draw the whole thing, even though I only want a portion of it. How about we let a equal 0 and b equal pi over 2, right? Then what I believe I have just discovered is that the area of that circular sector is b minus a over 2. Pi over 2 minus 0 over 2, which is, that's pi over 4. Is that right? Is the area of this piece that I've now cross-hatched 1/4 of pi? Well, I hope you remember that pi r squared, which in this case would be just pi, is the full circle, and that's 1/4 of the pi. Yeah. So that's makes it plausible that this is, in fact, the right thing. I guess maybe I should say, trust me, this is the right thing. So it's not just r of theta that needs to be dealt with, it's r squared. And finally, let's take this on to the sort of its complete fruition when there's two functions involved. When there's an outside bound and an inside bound, and we're getting the area for the piece between those, and also between two angular limits. All right, so I tried to draw a pretty careful graph of kind of the generic situation we're thinking about, where we've got two functions where r is a function of theta, although I made one of them easy just for the sake of convenience so that we have a nice region. So I'm using the blue thing as a cardioid we saw just a minute ago, and the second thing is a circle of radius 1. You want to think about dividing this thing up into circular sectors that start out, it seems, like they're just going into this point, but this point is sharper than you think. If you're heading out in this direction, you're going to be talking about a region that's like this. Out here, you might be thinking about a region in there. Of course, I probably should show them with roughly the same d theta or delta theta. But in all positions, there's a difference between the radius, or the area that's enclosed by the red graph, and the area that's outside of the blue graph. Well, I should say that the other way. The area inside of the blue graph taken away from what's inside of the red graph, that'll be this area that's in between them. And I kind of like the way that thing looks because I think it's one of, well, it's close to being one of the symbols they use in Star Wars for the, I think it's the good guys, the Rebel Alliance. Right? I've drawn over this so much that it's hard to see, but it looks, I don't know, maybe a little bit Batmanish too. Except those things come all the way up to the corners. Anyway, how do we get its area? Well, you want to have the area from A to B, the integral from A to B of the first thing squared, which is just 1 squared, d theta. Yep, and there's that 1/2 I always forget. Minus the integral from A to B of the other thing squared, and with its 1/2 too. Now the other thing is 1 minus cos theta. So we need the integral of that thing squared. Because of the properties of integrals, you can combine this into one thing. I'm thinking maybe I want to FOIL rule that out too. And you get 1/2 the integral from A to B. It'll end with d theta. When I FOIL rule this guy out, I get 1 squared, which is going to cancel with that one because we're subtracting. And then I get minus 2 cos theta. Well, again, we're subtracting, so that'll be 2 cos theta. And then plus cos squared theta. And that's actually being subtracted. Right, so that's that's 2 cos theta minus cos squared theta d theta. I guess before I go too much farther, I'd better say what are these endpoints? What are the limits on the integration going to be? We're trying to get a region that starts off over here and goes all the way around and then ends up here. It's basically, I'm asking us to think about how to find the points of intersection of the two curves. This one, it's visual. You can just see that they intersect on the y-axis. That makes sense. R is equal to 1 all the time on the red curve, and when the angle is such that cosine is 0, which happens at plus and minus pi over 2, you'll get 1 out of the other thing's R formula. So the R's agree when theta is plus and minus pi over 2, which means that's the limits we should use. A and B are plus and minus pi over 2. Hey, here's a nice shortcut. You see how this thing is symmetrical around the x-axis? The top half and the bottom half are mirror images. We can just go from 0 to pi over 2 and double it. And that'll be nice because we also already have this 1/2 out here. So I think it's a good idea to re-express the integral I want up here in the corner. The area we're after would be the double of 1/2 of the integral from 0 to pi over 2 of our one function squared minus our other function squared. Oh, we'd already simplified that, sorry. 2 cos theta minus cos squared theta d theta. All right, well, the first bit of that we can definitely integrate. Remember how to integrate cos squared? You have to use the, I don't know if it's double angle formula or half angle formula, I forget the names of them, but it's that the cosine squared is 1 plus cos 2x over 2. All right, so let me make that substitution. Actually, let's first break this up into two integrals. 0 to pi over 2 of 2 cos theta, and then minus integral 0 to pi over 2 of, well, yeah, now I'm going to do the substitution I just said about. It's cos squared is 1 plus cos 2x. Or cos 2 theta over 2 theta. All right. Not so bad. This breaks up into, well, actually, let's go ahead and take care of this integral. If I integrate cosine, I'll get sine. And so we were looking for sine of theta evaluated between 0 and pi over 2. We should break this guy up into two integrals, one of which is the integral of a half. So that's 1/2 theta between those limits. And the other, it's also minus because of that, it's a cosine of 2 theta over 2. Let me take the over 2 out of here. D theta. Again, that's 0 to pi over 2. Well, we're almost there. We just need to do a U substitution. If U is 2 theta, du is 2 d theta. So I want a 2 out here, and that means another 1/2 out front. All right, so we've got, let's go ahead and evaluate these. Sine of pi over 2 is 1. Sine of 0 is 0, so this is 2 times 1. And, well, 1/2 of pi over 2 is pi over 4. At the lower limit for evaluation, you get 0, so 2 minus pi over 4 minus 1/4. This was u du. Oh, let's go ahead and, should I change the limits or should I change the, undo the substitution? Let's go ahead and undo the substitution. We had cosine of u du, so its integral is sine of u, right? But u is 2 theta. Right, so at the lower limit, sine of 2 times 0, that's still 0. And at the upper limit, sine of 2 times pi over 2, that's sine of pi, which is also 0. In other words, that term goes away. And we end up with 2 minus pi over 4 as our final answer. I have to fess up to something. I walked away from the board really a little bit nervous about whether I'd gotten that right or not, and I did. So I went into the computer and actually just ran it on Desmos, but that is the correct area. And I checked it 2 different ways, so we didn't mess up. Woohoo! Yeah, so the last thing we want to deal with today is figuring out arc length along a curve that's defined in a polar fashion. Again, I want to talk about thinking about the general parametric equation first. So if you have some graph where your position is a function of time in the x-coordinate and some other function of time in the y-coordinate, and you're at some particular time naught, time 0, right? That means your location, I should say something like at t0, you're going to be at f of t0 comma g of t0. And if you think about moving slightly into the future, a little differential amount of time, you'll be at a new location. And that new location is basically, well, it's in the direction of the tangent line. That made it look like it was curving more than we should. When you get into the point where you're thinking about differential lengths, every curve looks straight. You've magnified it so much that you're looking at a piece that looks like just the tangent line. So what's the tangent line look like? Well, it's a line where from your t0 position to your t0 plus delta t or dt position, you have a change in the x and a change in the y that are the derivatives. Let's see, we're using f for the time, for the x coordinate, so f prime times dt. That's how long that is, and this direction is g prime of t times dt. Actually, I should say t naught on these because we were thinking about evaluating in a particular t naught, right? So the time changes from t naught to t naught plus dt, but we want to know how much length is there in here? How much is that arc length, or what we call ds? And it's the square root of the sum of the squares, right? Because it's the hypotenuse of a right triangle, a minuscule right triangle, but still a right triangle. So ds is equal to, well, let me do this whole calculation. You have f prime at t naught times dt squared plus g prime at t naught times dt squared, square root of that mess, right? That's what ds is. Take this little cup out of the way. You see how you're going to get f prime squared and dt squared, g prime squared and dt squared? There's a dt squared in both of those, which can be factored out. And in fact, since it's squared and it's under the square root, you can pull it outside of the square root and just call it dt. And what remains inside the radical is f prime squared and g prime squared. So that's the thing that you need to integrate in order to get, that's differential arc length. And if you integrate that from one time to another time, you will get the arc length along the curve between those times. Let me just make it clear. I'm talking about here's t equals a, here's t equals b. There's this weird curvy thing that is measured along the curve. Between those things, that's how I call it L for length, right? And L is equal to the integral from a to b of the thing I just told you. F prime of t squared plus g prime of t squared dt. Now, if this is something you can evaluate, you're all set. And if it's not, well, as was the case in xy coordinates, often arc length integrals are just too hard to do. So you jump over to numerical methods if you need to. So what about polar? In polar, we have that the x coordinate is a function of theta, really, and it's some function for the radius, called r of theta, times cosine of theta, right? And the y thing is also a function of theta, and so that'll be r of theta times the sine of theta. So this is really just a parametric form where theta is the parameter, and we have the same thing, r of theta appearing both in the x and the y coordinate, but with different trig functions next to it. We're multiplying, so again you end up using the product rule to take derivatives. I just realized I've changed my tune a little bit, where I switched to a function called x rather than saying x equals f of x. Let's undo that, because that may be confusing. So think of this as x is some function of theta, f of theta, and y is some other function of theta. But they're both really these guys. So our differential arc length is still the square root of f prime of theta squared plus g prime of theta squared d theta. Theta is just as good a parameter as any other letter is, so you're just thinking of this as the same thing as in the parametric form, but to figure out f prime, I'm actually going to need to use a product rule. Alright, so yeah, our first derivative of arc theta times cos theta is going to be, let's write all this out. The derivative of the first thing, which is r prime of theta, times the second thing, plus the first one left alone times the other one's derivative. Cosine's derivative is minus sine, isn't it? That is just f prime, so that needs to be squared. Have I got room for the other guy? I hate myself here, but think about this as just a continuation of the radical. That's because we're going to need to have g prime, which is the first guy's derivative times the second guy, sine of theta, plus the first guy left alone times the derivative of that one, which is cosine of theta. So that's the end of our radical right there. No, it's not, because we need to square this. Then it's the end of our radical. And then finally we have a d theta on the f. Well, fortunately this thing can be simplified a bit, but the main problem is that we're going to need to FOIL rule out some things. Yikes. Okay, so first times first. That's r prime squared cosine squared. Outer times outer and inner times inner are both the same, and they are the negative of r times r prime times sine theta times cos theta. Right, and then last times last, and this one is plus r squared theta, sine squared theta. I was trying to indicate that this was a radical that just starts there and keeps going. So it's going to need to go over a line break and keep going. Apologize for that. But we also need to have the square of this other thing. First times first there is r prime of theta squared times sine squared theta. Outer times outer and inner times inner are very similar to what they were up above. Similar? No, they're the same, aren't they? It's r prime times r times sine theta times cos theta. R prime, r, sine theta, cos theta. Huh. Except this time it's with a plus sign, right? Because we don't have one of these positive and one of them negative. They're both positive. Right, so I'll write it down, but we're just going to cancel it in a second. What is going to survive is r of beta squared times cosine squared. I just have space for that. Okay. And then that's what's under the radical. Sorry, off the end of the board, there's a d theta. All right, like I said, this stuff here from the outer times outer and inner times inner terms, they cancel each other. The other thing that's kind of cool is r prime is times cosine squared and also times, r prime squared is times cos squared and times sine squared. And when you add up cos squared and sine squared, you get 1. So this whole piece becomes just r prime squared. And the same thing happens down here. You get a sine squared and a cos squared, which you can sort of factor the r of theta squared out of. And you get, well, look how much simplification we get out of that. Our differential arc length now is the square root of r prime of theta squared, because those became 1, and then these all canceled, and that became r of theta squared. D theta. Isn't that amazing? So we just find the derivative of the r function and the function left alone, square root of the sum of the squares of those things with a d theta on the end. That gets you your differential unit of arc length. All right, so let's check. Well, no, let's finally say how do we get actual arc length? You integrate between the limits, this quantity. And that'll be the length of the part of the curve that goes from t equals a to t equals b. I said t, didn't I? Theta equals a to theta equals b, because our parameter here is theta. We're in polar coordinates. All right. What's a nice example of this? I could figure out the arc length along a circle. That's probably the extent of my abilities at this hour of the night. How much arc length is there along a circle between theta equals 0 and theta equals pi over 2? The full circumference of a circle, well, depends on the radius, doesn't it? But let's suppose we've got a nice radius, r is 1. The full circle is 2 pi, so this is pi over 2. Yeah, in fact, we know that. That's what radian measure means, right? The arc length along a circle of radius 1. So we should get pi over 2. What I'm doing is taking the function, r is 1. So what's its derivative? 0. And what's its function? 1. So we've got the square root of 1 squared. Oh yeah, so this is just telling us that the length would be the integral from 0 to pi over 2, the square root of 1 squared d theta. That's just theta. That's, well, when we integrate, that's just theta. And so we get theta evaluated between the limits, we said. So sure, it's pi over 2, but that wasn't very exciting because I didn't really see much of it. How about we do that cardioid? That would be a better example. And I'm not feeling quite that wimpy that I want to stop after just getting you that a quarter of a circle is pi over 2. That's lame. So remember what the cardioid's equation was? It was r is 1 minus cos theta. And that was a graph that looked sort of like a heart, something like that. It has this sort of tip that bumps into right at 0. If I want the full length of it, I guess I could go all the way around 0 to 2 pi, but I could just double half of it. It is symmetrical top to bottom. So I'm going to say the arc length all the way around the thing is 2 times the integral from 0 to pi of, well, we're going to need that polar coordinates formula, so I better work out what r prime is. If r is 1 minus cos theta, r prime is 0 plus sine theta, right? Cosine's derivative is minus sine, and that might, yeah. plus sine theta. So it's sine theta. Great. So we need the square root of r prime squared, sine squared theta, plus 1 minus cos theta squared d theta. I think I'm going to get this to work out. Let's do a little algebra under there. That's let me do the copying first. 0 to pi square root of sine squared theta, and then FOIL ruling that baby out. It's 1 minus 2 cos theta, right, plus cos squared theta. D theta. Yeah, so this is a 1 with that, right? And there's another 1. So what we've got there is integral 0 to pi, the 2 in front of it, square root of 2 minus 2 cos theta. Well, I shouldn't have gotten so cavalier. I can't integrate that. Well, that's what I always keep telling you. These arc length integrals come down to things that you can't necessarily do. What I think I would do is go turn on Sage, and I think I still have Sage running in the next room, so we'll do that numerically and get a decimal answer. Well, this is embarrassing. When I went in and asked Sage what to do with it, it had no problem integrating it symbolically, and I'm not going to be beaten by a computer. Actually, I've already been beaten by a computer, but still. The thing I didn't recognize here is that we've got a hidden double angle inequality, sorry, not inequality, double angle formula. The thing I want to use is that 1 minus cos theta is the same thing as sine squared of theta over 2. I guess that's a half angle formula. Not quite. Sine squared of theta over 2 would have an amplitude between 0 and 1. So it would have an amplitude of a half. Whereas this has an amplitude of 1, right? 1 minus, no, yeah, amplitude of 1, the total height, peak to peak height is 2. So we need a factor of 2 here. Now, I actually did this on my graphing calculator, so or double check that I got the things in here. I can show you. I plot 2 times sine of x over 2 squared, and I plot 1 minus cos of x, and they look like that, one thing right on top of the other. So, yeah, so this is good stuff. That means that this piece under the radical is 2 times that, so it's 4 times sine squared theta over 2. All right, we can proceed then. We've got 2 times integral 0 to pi square root of 4 times sine squared theta over 2. Theta over 2 is what's in there. Good, and then d theta. And the point of all that is that this is a perfect square underneath the radical. So you can just pluck it out of there. It becomes 2 sine theta over 2. I need a d theta to match with the theta. In other words, I need to do a U-substitution. So if U is theta over 2 du would be d theta over 2. So let's divide by 2 and then times by 2 as well. There's a lot of extra 2's floating around. Feel like we ought to take this 2 onto the outside too. Yeah, I think it's fair enough to just pull all these 2's together and write 8. All right, so sine of theta over 2, that's sine of u du. The integral of sine is minus cosine. So we're getting 8 times the negative of cosine of u, which is theta over 2, evaluated between these limits 0 and pi. Well, hopefully, I'm worried about that minus sign, but let's see if what happens with this. When theta is 0, theta over 2 is still 0, and the cosine of 0 is 1, and so this is a minus 1 here at the lower limit. Minus 1, right? What about at the upper limit? Then, when theta is pi, we're talking about the cosine of pi over 2. Cosine of pi over 2 is 0. That's kind of good. So we get 0 plus 1 times 8. Wow, it comes out to 8. Well, now I don't know because I got a symbolic answer before, but I think it's probably right. Just to reassure you, the computer agrees, it's 8. All right, well that's the end of our fun for today. Getting this posted a little bit later than I'd hoped, but it should still easily be up there by 9:30. So I'll send an email with a link as soon as it's available on YouTube, and I'll see you tomorrow.